have a low specific heat capacity? If you're not laughing at that joke, then you probably don't understand the physics behind it, so allow me to explain. Let's say you had two different substances and you applied the same amount of heat energy to each of them, but they ended up at different temperatures. What would you do? Most people in this situation would of course resort to blind panic and throw themselves out the window, but you're a physicist. You can reason. So what could be the reason? Well, they could have a different mass. A larger mass requires more heat to raise its temperature. They could have different surface areas, so a big surface area would be able to absorb more heat. They could be painted differently, so a shiny material would reflect the heat away and not heat up as fast. But let's say all of those things were the same. What could be the reason? Turns out, the type of material. And this links into something called specific heat capacity. Specific heat capacity is the amount of heat energy required to change the temperature of a 1 kilogram mass by 1 degree C. And to show you a bit about how that works, I've got a demonstration at the front. So I'm going to move you round to here. Now, in my left hand here, I have got a 2-pence coin, which I've actually ruined by heating it so much. And in my right hand here, I've got a 10-gram mass. These two materials are made of a slightly different type of steel in the main part of their body. And what I'm going to do is I'm going to put each of these different materials under an identical Bunsen flame. Okay, the hottest part of the flame. This. And so what I'm doing is I'm applying the same amount of heat energy to both of these materials. Now, they've got more or less the same mass, so that can't be a factor. And they're more or less the same surface area. So the biggest factor here is the fact that they're made of a different type of steel. And what that should mean is that whichever of these materials has the lowest specific heat capacity is least able to store the heat effectively and will rise in temperature faster. That material will reach a temperature that we're going to call red hot faster than the other one. And as you should be able to see right now, the 10-gram mass in my right hand has comfortably reached a temperature of red hot. This has a lower specific heat capacity and has therefore raised its temperature faster. Allow me to give you a little analogy of how that works. For that, I'm going to have to rotate you back to the front of the class. Perfect. These two containers are going to represent our two metals. So this measuring cylinder is representing something with a low specific heat capacity, and this is something with a high specific heat capacity. The level or the height of the liquid in these containers is going to represent the temperature that that substance reaches. If I apply the same amount of heat energy to both of these substances, you should see that because this container, this material, had a lower specific heat capacity, it reaches a higher temperature. The level of water inside it is greater than the level of water inside that. So that's a good analogy for specific heat capacity. Now let's imagine that we kept on heating that 2-pence coin. Eventually you would start to melt the Queen's face, right? And it would turn into a liquid. And if you kept on heating it beyond that, it would turn into a gas. You'd vaporize the metal. When you're changing the state of a substance, you're no longer talking about specific heat capacity. You're now talking about specific latent heat. Specific latent heat is the amount of heat energy needed to change the state of a 1 kilogram substance. Note there is nothing about changing temperature. So if you were to heat a solid and turn it into a liquid and then keep heating it to a gas, the temperature time graph would obviously look like this, right? Wrong! You fool. No, the temperature time graph would look, at least to start off with, something like this. So you have a solid and you are applying heat to that solid, just like we did at the front. You're making the particles move more quickly, and therefore the solid gets hotter and hotter until the temperature starts to plateau. And at this point, the energy you're putting into that solid is no longer making it get any hotter. Instead, the energy you're putting in is going to breaking the bonds between the solid particles and turning that into a liquid. This is the stage of specific latent heat. If you were to continue adding heat once everything had melted, you would just raise the temperature of the liquid, right, making the particles move more quickly until you hit boiling point. Once again, the temperature plateaus off. The heat energy going into this is not going to making the particles move any faster, but going into breaking the bonds between the liquid particles, turning it into a gas. When you're going from solid to liquid, or liquid back to solid, that's the specific latent heat of fusion. Not to be confused with nuclear fusion, okay, so this is like an ice cube melting, not a hydrogen bomb. And liquid to gas, and gas back to liquid, is the specific latent heat of vaporization. Now, latent is actually quite a good word for this. Latent is Greek for hidden. I'm obviously a classics teacher in my spare time, although that is the only Greek word I know. Anyway, latent is quite a good word because it means hidden. So you're not actually seeing the heat do anything in terms of a rise in temperature. Okay? It's just changing state. Now, I know that's a lot of new words, so let's to make ourselves feel better, go and melt some stuff. Okay, follow me. Although you don't really have a choice because you know I control the camera. Okay. So for this last little demo, I'm going to turn that off. Specific latent heat of fusion. I'm going to add some solid paraffin wax pellets to this beaker. See them dropping in there. Okay. So that is solid paraffin wax. And I'm going to heat this solid paraffin wax over a Bunsen flame. Now note by doing this, this is the specific latent heat of fusion in action. I'm adding heat to a solid, and in doing so, I'm converting that solid into a liquid. All of the heat now is going to breaking the bonds between the solid particles. Okay? Takes a little bit of time to do this, so I'm just going to do my awkward silence face. Okay, that took long enough. So that's now all melted. So I'm going to take that away from the heat source and turn that off. So as you can see, specific latent heat of fusion, I've turned that solid into a liquid. Now if I wanted to turn that liquid back into a solid, I'm going to need to remove the heat, right, from the system. And to do that, I'm going to pour it on this metal plate. Okay. Now, bear in mind that you had to put heat in to break the bonds of the solid, turning it into a liquid. So it stands to reason that you're going to need to take heat out of this in order to turn it back into a solid again. Okay? This is still the specific latent heat of fusion in action. It's just going the other direction. The bonds are now reforming. And you should see, I'm just going to see if that's correct on camera, the white splurge on the plate clearly representing we've gone back to a solid. Lovely. Okay, so I'll tell the joke again, and this time obviously you'll get it and you'll laugh. Is it hot in here, or do I...